This chapter is a continuation of the previous two chapters. Nothing here is going to be new. It's simply applying the old stuff. Now, first thing we're going to do is a very familiar question. Let's say we have 0.10 molar HClO2, we have a Ka, we want to know what the pH is. Easy, we can do this, we know how. We write our nice equilibrium, we do our icebox, we have our K equation, can't neglect X, that K is probably too big to do that. So we go through the whole process and we get a pH of 1.55. I'm sure you can all do that. Now, the question that's going to come up in this chapter that's different is this one. Again, we have 0.1 molar HClO2, but this time we're also mixing in some 0.10 molar NaClO2. We've got an acid, but we've also got the salt of the acid. This is called the common ion effect. That is, we have two of the same ion in solution. Now, just again as usual, the first thing you're going to have to do is write an equation. Again, we're going to figure out pH. There's my equation. Don't try to react them. Don't try to say HClO2 plus NaClO2 equals and make up some weird random product. That's not what's going to happen. HClO2 is going to do this, just like it did in the previous problem. NaClO2 is a salt. All it's going to do is dissociate. Once again, Na plus, totally we can ignore it. Very, very, very weak. It's going to just sit there and be a spectator like Na plus always is. So, ClO2 minus is going to be in solution. There's going to be more of it. So look at my icebox. Initially, I have 0.10 molar of that, HClO2, but I also have 0.10 molar of ClO2 minus coming from the NaClO2. That's what makes this different. I've got not 0.1000 like I did over here. Here, I now have 0.10, 0.10. Common ion effect. Now let's think about this from a Chatelier point of view. I've put in more of one of the products. Shift should be back this way, right? Let's see if that's true. Here's my whole ice box. Again, minus x, 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 0.10 minus x, x, but now this one is 0.10 plus x. Look at the difference. Think about what the old icebox was. Here's the new one. So now, look at my equation. 1.1 times 10 negative 2 equals x times 0.10 plus x over 0.10 minus x. Not x squared on top anymore. Once again, I'm not going to be able to neglect x. Next video, I'll give you something that you can neglect x. But for right now, we're going to have to do this the long way because that's too big a number. But I'm going to do my usual, combine like terms. I'm going to multiply both sides by the denominator. Then I'm going to combine like terms. You can check all this math yourself later. Finally, I get a nice quadratic, which I can solve for x. Notice my icebox. X is, again, the H plus concentration. And a pH of 2.03. Look, exactly what we predicted. This is a smaller number. 9.15 times 10 negative third is smaller than 2.81 times 10 negative 2 that we had in the previous problem. Where the pH back here was 1.55, the pH in the common ion effect problem is 2.03. The shift has indeed gone to the left. The dissociation is not as much because I've got the common ion. That's the whole idea of the common ion effect. The pH has been raised.